So stroke people, let's say this guy or person has problems using their right hand, okay? They find it very difficult to groom themselves. So how are you going to teach this person to use a toothbrush? Through repetition of doing it, okay? So how do you take a toothbrush, the activity or the skill of picking up a toothbrush and brushing your teeth, how do you make it harder? And that's why Gentile's taxonomy was developed. So you look at the task, you sort of evaluate the needs or sort of where the person is in terms of like their abilities, and then you put the task as like 1B or 1C or 2A, and then you can go step by step, and it gives you a guideline how to make the action that you are trying to train this person incrementally more difficult. Does that make sense? So for example, you would think about like every time they do the trial, you would have no change in where everything is. Or if you started wanting to make things more difficult, you would introduce intertrial variability. You may want to, depending on the skill that you're going to look at, you may want to introduce, environmental regulatory conditions that are changing, for example, or have a person moving, or, there's lots of different ways based on the taxonomy, how you can make something more difficult. But that taxonomy is a good guideline, especially for, we use a lot of sports examples, but it's especially helpful in sort of a rehab setting. Does anyone have any questions about any of the material or specifically Gentile's taxonomy based on what I just said? Everyone's good? Okay. So today what we're going to be doing is we're going to be talking about the measurement of motor performance. And so the topic of this the topic of this particular lecture is evaluating how we as researchers, so we have now evaluated that for our learning, so in motor control and in motor learning, we are going to have to develop a method to grade motor skill performance. And it's based on that grading ability that we're able to look at what variables affect our ability to do motor skills. It's going to allow us to infer how we control our body to regulate movements or motor skills. And so if you think of science, right, you need sort of a value to evaluate, right? Like think about like randomized control trials. You have a drug and one person gets a placebo, one person gets the drug. And then you look at outcome measures as to who got better. And if it's significantly better, then obviously the drug worked. It's a little bit different with motor skills because, like we said last day, it's difficult to sort of develop guidelines as how to study them. So this lecture is now that they've developed, breaking down actions, movements, and neuromotor processes, let's talk about the different ways that we can actually grade or evaluate motor skills, and that will allow us to conduct research in it. So what we're going to be doing is understanding the need for measuring of motor performance. We're going to be talking about performance outcome measures, performance production measures, neural measures, and then we're going to finish off with motor abilities. So measuring motor skills is a lot more sort of like difficult than you would think intuitively. And so I want to pose a question to all of you is what characteristics could you measure to perform the following motor skills? Okay. So here we have an example of serving a tennis ball. So let's see if no, it didn't make work at all. Is it gonna work? I may have just effed it. Play. If I do this and play it. Okay, so it's working. So everyone watch this video. And what I want you to do is think about different ways you can evaluate the performance of this person's serve. So we're looking at it at different angles. Let's look at it again. Was it frozen for everyone? That's annoying. So how can I get you the link? Do you guys want to? I mean, that's kind of lame. I kind of wanted to like video with you guys, but do you guys want to all look at the? Do you guys all have your lecture slides open? Watch the video for me. I thought by embedding it, I could actually like have it play, which is kind of annoying. What do I know? So anyone who's watched the video, Apollo, maybe go to the slideshow. See, that's what I did. I opened it, I made a slideshow. Okay, so slideshow, and then I pressed play. Did it work that time? No, I don't know, man. I have the link. I wish I could like figure out how to do this. Oh, preview? Wait. What about now? No, sorry, Ronnie. I put it in presentation mode. Yeah, you're welcome. Who with the prof? Okay, let's watch it again. Dude is serving. So think about this. So part of the problem with measuring motor skills is that it's hard to grade someone. How would you grade potentially a tennis serve? I mean, there's no right answer. You could do it in lots of different ways. Give me some examples of what you could do to grade this person's serve. Yep. Racket speed, speed of the ball, whether or not it like was accurate. I think they're aiming cross court. Their form, maybe. Yeah, the biomechanics, right? So the point of what I'm trying to say, yeah, exactly, right? The point of what I'm trying to say is that there's a lot of different ways to try and measure this person's performance. And so that's difficult. It's easier in sports setting because typically sports are associated with like a particular goal, right? Like a particular outcome that is like sort of visual, right? Now, let's think about what happens if we use a clinical example. Now let's watch this guy. Preview video. Bam. Okay, so walking would also be a motor skill. Now, in this case, we're evaluating someone's detriment in performing a motor skill, in this case, walking, as a result of a neurological impairment, or they had a stroke in this case. So let's watch this person.
Patient has suffered a stroke affecting the right side of the body. Notice how the arm is held in flexion and the leg circumducts, moves in a bit of a circular fashion on the right side as he walks. Classic for upper motor neuron dysfunction.
Want to watch it again?
Patient has suffered a stroke affecting the right side of the body. Notice how the arm is held in flexion and the leg circumducts, moves in a bit of a circular fashion on the right side as he walks. Classic for upper motor neuron dysfunction.
So what do you guys think of ways that you could sort of measure this guy's performance in walking? Because if you're going to evaluate if he's getting better, right, you need a measurement to be able to say, okay, well, this measurement is increasing. What did you notice about his walking? Yeah, there's no wrong answer, right? How straight he is. You can see that the right side of his body wasn't really moving, right? Like it's spastic, so it wasn't swinging. So you could you can evaluate his like coordination or his body dynamics in that sense. You could look at like how long he can walk without falling, how fast he's walking, step distances. Yeah, totally. Balance, lots of different ways, right? And so that's the problem, or sort of a factor in evaluating motor skills. Yeah, bilateral symmetry, right? So what you would want to do is think about like doing research when they're going to now evaluate motor skills. They first got to start off from the bare beginning, and they're going to say, okay, let's look at a motor skill, and then how well someone does, we'll grade it. We'll start changing variables like make different choices or make them have to move faster or change different variables, and then see how their outcome is. If it's worse, we've figured out something that makes a motor skill harder. If it's better, we've figured out something that makes the motor skill easier, right? And then we're going to have to study different motor skills, study a whole bunch of them, and then look at if there's any similarities, and then they can start grouping things together. That's how they sort of started off this science. Does that make sense, everyone? Everyone good? Boom. Oh, shit. Okay. So the reason why they're important is specifically that, right? We need to assess someone's performance. So this is going to allow us to evaluate their overall capabilities and limitations. So if you think about a stroke patient, by giving performance, we're going to be able to see what, like, get up to a point where they can't do stuff, and then that's going to give us a guideline as to where they're standing in terms of their neurological impairment. Or even with like sporting, like think about coaches, right? They want to get to see where their sort of like students or their athletes are at, and then it's going to give them an idea of what they should be training. It allows us to sort of measure or determine progress, and then it allows us to also give an idea of or infer areas of dysfunction. And I had mentioned in the previous slides that this is like sort of imperative for research because we need to quantitatively measure performance to sort of go through a sort of our scientific method. It allows us a basis of studying motor control because we can look at different variables that would improve or decrease performance, which is going to give us an idea or allow us to infer sort of like the specifics of human motor control. So there has been, like we just did with those examples, there's a bunch of different ways that you can evaluate performance, right? And research has sort of developed two different categories as to what sort of measurements that you can utilize for different motor skills, depending on what they are. You can use performance outcome measures, which are going to be concerned with the outcome of performance. And then we're going to also have performance production measures, which are going to be more concerned with the movements that entail the motor skill as it's being performed. Right? So we're going to use different measures depending on what sort of part of the motor skill we're going to be evaluating. Is it the skill itself? Are we going to be evaluating the movements or the actual individual coordination of the body? Or are we going to be looking at neuromotor processes? Depending on our research, depending on what we're analyzing, depending on what type of learning we're doing, any one of those could be the most important, or all of them. So let's first talk about performance production measures. These are going to be those measurements that are sort of indicating the outcome or the result of someone performing the skill. So the common example would be sort of like a score. So here we have like I think they're gymnastics or figure skating judges. So this is giving us an overall score. So this is an example of an outcome measure because it's a score detailing the outcome of a particular performance of a motor skill. Other examples could be like the distance you've thrown a ball, slap shot speed, batting average, marathon time, running speed, for example. These are all sort of, and there's going to be a whole bunch of different ones, right? Anything that you come up with. These are all measurements that are going to be sort of telling you how the outcome or how the person performed in terms of their outcome. However, things that outcome measures don't measure are the individual movements. So outcome measures give you sort of the overall achievement in accomplishing the goal, but they don't really tell you like, so for example, so let's say this person got a 76 out of 100 on figure skating. It doesn't really tell you if they did like, you know, like a triple sow cow or like a flip, or it doesn't tell you about any of the movements that was sort of occurring during the performance of the skill. It just gives you an outcome ultimately. And so performance production measures then are going to be more concerned on providing values that sort of detail the movements or the neuromotor processes. Performance outcome measures are more concerned with the outcome of the actual skill itself. And so in this slide, it just details just that. Performance production measures are more concerned with the production of the skill. So that would include things like the individual movements that were utilized to achieve the task, as well as the specifics or the individual specifics of the neuromotor processes that were used in controlling the body during that motor skill. Because, like, for example, let's do running or soccer, or anyone that's learning a sport. Initially, they are uncoordinated, and then eventually they become better at controlling their body. That's like sort of almost like a movement or a neuromotor process sort of measurement. And it's going to highlight how they're changing, I don't know, how potentially the movements or their coordination is improving in learning a motor skill, whereas the outcome may not necessarily change that much. Does that make sense, everyone? Now, in this slide, I've taken it from the textbook. These are just sort of examples of different performance outcome and production measures. So examples of outcome measures would be time to complete a task, amount of error, number or percentage of errors, number of successful attempts, time on-off target, time on-off balance, distance, for example. Whereas things like performance production measures would look at the actual movements themselves. So displacement, velocity, acceleration, joint angle, joint torque, EMG, EEG, which is brain activity. And these are also looking at what parts of the brain are active. So these would be more neuromotor processes. Does everyone get that? Boom. Ooh, sir. Yeah. Okay. So ironically, I don't know, that's not really ironically, but interestingly, the most at the first and most utilized outcome measure is reaction time. So that was the first one that was used in motor control research, and I'll tell you why. The actual measurement itself is indicating how long it takes the person to initiate movement. So do you guys know what reaction time is? Like, if you give someone a go signal, there's an amount of time where it takes the body to sort of process and then figure stuff out before it gets going. In motor control research, reaction time was the first and probably most common measurement. And because what it would do, it would allow researchers to, okay, we get someone to do a task, check the reaction time. Now, change a variable. If the reaction time increases, it made it harder. If it gets smaller, whatever you changed made it simpler. So then you make a list of things that make things more difficult for that motor skill versus things that make it easier. And then you can get an idea of, oh, increasing the number of choices makes things difficult. So that's a factor in how we process or sort of control our bodies. We have to process everything together, develop a plan, and then we can execute it like a computer. Boom. So here's an example in terms of reaction time. What is the minimum reaction time allowed for a legal start in a 100-meter sprint? So the answer is 100 milliseconds or 0.1 of a second. Anything lower than that is illegal because it's too quick of a reaction time. Does there any sprinters in the class? Marco, you sprinter? Only to the still counts. Interesting. So here's an example of how reaction time is utilized in sort of sprinting. So in Olympic runners, just so there's a force plate at the end of like they see these starting blocks. Can you guys see that? So it's all electronic. So if they notice that the foot comes off of the pedal in less than 100 milliseconds after the starter pistol was initiated, then they know that it's a false start. So do you guys remember how people can get disqualified because of a false start? Before you got one false start and then the second one you're kicked out. Now you just kicked out. It's because people are anticipating. They're trying to anticipate when the start pistol is gonna like get shot, and then so they're trying to get like a head start. So like I said, reaction time is used in motor control research as an index of the specific aspects of human performance that are sort of altered by changing different variables in the environment. So reaction time in itself in motor control research is used to infer what a performer does to prepare an action. Because let's say you change something in the environment and all of a sudden the reaction time got more. It somehow that processing took longer. So whatever you moved made it more difficult for the brain. So by checking reaction time, it allows us to understand what the person is sort of contemplating or looking at, evaluating when they're initiating movement. So we can identify what things in the environment the person is looking at or the performer is requiring to process. And then it allows us to assess the capabilities of a person to anticipate a required action or to determine when to initiate it. So here's an example of how reaction time is sort of utilized. So there's 3 different types of reaction time. Simple reaction time is when you have a go signal and that requires one response. So example, like a sprinter in a race, you hear the tone or the gun and you go. Okay, so that's going to be associated with a particular amount of reaction time. Choice reaction time is when you have more than one signal and each requires a different response. So an example would be like a traffic light. So you have 3 different lights. So you have green, yellow, and red. So what green means go, red is stop, yellow go faster, right? So now you have 3 choices. What research has shown us is that the more choices you have, the longer the reaction time is to initiate movement, meaning that your brain has to evaluate the different choices and then figure out which one is the most appropriate for whatever the stimulus was. So the reaction time for a simple one choice example would be a lot less than the reaction time associated with choice reaction or a choice option. And then the last thing is discrimination reaction time, which is similar to choice reaction time. However, there is more than one signal, but only one involves a response. So now it's not 3 options, 3 responses. It's 3 options, 1 requires a response. So this is just a visual to sort of demonstrate that. Simple reaction time, stimulus, response. Choice reaction time, 3 different stimulus or 3 different sort of options. 3 responses, whereas discrimination, there's 3 different stimulus, but only 1 requires a response. These are the different sort of things that were utilized in research to sort of evaluate what variables would affect reaction time. Now, what was done in research is that they used EMG to determine when the muscles were turned on. So let's say we were doing a reaching task. So when the stimulus started, then you would have to reach and grab something, for example. They would put EMG on your arm, and then they would take the reaction time from the reaction time is the quiet period before, is like from the stimulus onset before the initiation of movement. So there's going to be an associated time in that. If you take EMG, it can fractionate or divide up the reaction time into the pre-motor and motor time. So if you look at reaction time, can I just go up a slide? See here we have EMG. There's an amount of time, like a very small amount of time, but there is an amount of time where you have EMG activity without movement because you have to get the muscles to contract. It contracts and then there's a like sort of like a delay before the muscles or before the limbs start moving. Does everyone understand that? Because the muscles have to contract, right? Like, yeah, I gotta get the system going. So if you use EMG, you can look at when the actual EMG activity started, and it gives you a better idea of what was actually just brain processing. So here we have reaction time. So here would be a stimulus onset. This is just an EMG recording, but this would be the beginning of observable movement. So let's say this example was that reaching task. So you have EMG on the arm that's going to measure muscle activity. And so from the stimulus onset up to the point where you can read EMG activity or muscle activity, that's going to be called the premotor component. That's all brain processing. So if you fractionate reaction time, you can change variables in the environment and look at how much time is required for the brain to process. Now you have a measurement that you can change different things and then look at what's harder for the brain to do. Right? Remember, this is all before MRIs and like before computers. This is they're trying to come up with ways to sort of evaluate this, right? It's like the 70s, 80s. A long time ago. And then the motor component of the reaction time would be the time where the signal's already been sent out, and then you have readable electrical activity in the muscle, meaning the muscles are starting to contract. Is that confusing for everyone? Or does that make sort of sense? Good. Makes sense, yeah. So that's why reaction time became the most popular outcome measure to utilize in research first. They used other things in like other measurements. You might see this. So if any one of you are reading the textbook, you'll see these variables as well. Movement time is the time to complete a task. So the amount of actual movement. So this is going to give you an idea if like it took longer to complete the task. So sorry, how long the person moved, how long it took the person to complete the task. So these two things. So movement time is the interval of time between the initiation of movement and completion of the task, so the actual time the person was moving, whereas response time is reaction time plus the movement time. And so these have been utilized in research because what we found, or what researchers found very quickly, is the speed accuracy trade-off. So if you're going to do something, let's say you are drawing or you're playing the piano or you are drilling something or doing something very accurately, what do you notice about the speed of your movement for everyone, generally? Yeah, and which makes sense, right? You want to make sure that you're accurate and you decrease errors, and so you slow down. So what we realized in research very quickly is that the need for accuracy causes our movements to slow down, and that was through using these two measurements. So here we have just the different terms that we had utilized all in one sort of graph. So reaction time right here. So this is the go signal, reaction time. And then movement time would be where it is the time the actual person was moving, whereas the whole thing from go signal to end of response is response time. But the most important of these is reaction time. And if we fractionate it, we can look at premotor and motor time. Premotor time would be all just brain processing, and then that signal going down the spinal cord into the nerves. So I was really excited to show you guys this. Can you all go on your lectures and click the link, please? Actually, if I stop presenting, I wonder if I can get someone to do it. Or, let me see if I can do this. I'm presenting. Okay. Okay, let's do this, guys. Okay, I'm gonna go here. Boom. Okay, I hope this works. Can you guys see it? okay. Everyone try it. I'll do it too. Yo, because I am a really fit 38-year-old. Here we go. So this is a sort of like just a game to show the word part. Adelaide. Did I screw this up? Oh. Okay, here we go. Hey guys, all right? Okay, so this is a little thing. I'm gonna check my reaction time. I gotta hit the screen when there's a stop sign or something. Oh fuck. Ooh. Okay. Okay. Here we go. 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 Boom. Okay. 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 There you go. What's up? What did you guys get? You need a better chair. Well, I mean, it's a stool, but I agree with you. 26. You got 26? No, you guys are lying. Oh, stop presenting. 18. Window. Okay, hold up. We got a problem. Can you guys see my can you guys see the presentation? Oh man, oh there it goes. Bam. Cool. So then my reaction time was like something like 400 milliseconds. So sort of terrible. But that gives you an idea of like the measurement, right? There's an actual time of processing. Like I see it, then it's got to like, I got to process it. To process it, I got to move my hand, and like there's like a time, right? So then you can evaluate different things and then see if the person's stressed, right? Stress changes the reaction time. So have someone like, you guys all like chirping me or like making me like, you know what I mean? Or like stressing me out, and then see how reaction time changes. Then you get an idea that, okay, when you're stressed out, that affects someone's ability to do a motor skill. You wouldn't know that unless you had a sort of outcome measure. Make sense, everyone? Your reaction time in saying yes is quite low. Okay, good. Awesome. Other things that can be used as an outcome measure, things like error measures, so how accurate someone was being. So error measures allow for the evaluation of performance on skills that have spatial or temporal accuracy goals, where they have like a time or space sort of goal. You can utilize these numbers to calculate error. And error allows us to assess both bias and consistency. And I'll show you what that means. So here we have, think about a trial where you got to do something in a certain amount of time. You can look at how their performance of the performer, how much error they had in achieving that goal. And so what you do is you develop a score of absolute error. And so you look at their performance minus the criterion, and take the absolute value of that divided by the number of trials, and it gives you sort of like a general like number for accuracy. So that's absolute error because they're using absolute values. You just to look at like whether that they overshot it or undershot it, you're taking the absolute value or the magnitude of their error and then averaging it out over the number of trials that they did. And then you get an average number of accuracy or their performance, right? So if someone gets better at something, technically their accuracy would improve. So it'd have less error. Constant error, it allows us for sort of measuring performance bias because you take out the absolute values. So if someone was undershooting or overshooting, you would keep the plus or minus. And then if the overall average is positive or negative, it gives you an idea that they tend to undershoot or overshoot the target, whatever it is, either it's spatially or temporally. Variable error is the standard deviation. You guys all took stats, right? So looking at the standard deviation, so the averaging of the distance from like sort of the mean, that allows us to look at consistency or variability. So how consistent they were in each of their attempts. So because maybe the average, like maybe they were all over the board, but the average just tends to be close to the goal. They're going to get a good accuracy score when really they were just terrible. So looking at consistency is important as well. And then if it is like, think of like darts or golf, if they have a two-dimensional sort of spatial thing like this, you can look at radial error, or like same thing, you're looking at distance, but you would be taking the distance from the goal and then using that and in the absolute error calculation. So here, let's like an example of how this kind of stuff is used. So here we have two golfers. Now, who would you say is the most accurate of the two golfers? So they each did like 6 trials. Yeah, because if you took the average of like, so you like did the average of all the trials for golfer A, it's going to be somewhere in the middle. Whereas if you took the average of golfer B, it's going to be off to the side, right? So A thinks he's real good, but it's just because the average just ends up being in the middle. So he's not very consistent because his standard deviation would be high. Whereas golfer B is fairly consistent. Like look at the difference. They all kind of went in the same area. However, he tends to just like sort of like go off to the right a little bit. So my man B, he's doing good. He's good, people. Does that make sense, everyone? Drew knows B. He knows him. You might be B. I don't know. I don't want to out you, but it might be you. So remember how we talked about continuous versus discrete skills? Skills that are like riding a bike. There's no real beginning or end. It just kind of continues on and on. Another example would be something like driving a car on a highway. Now, what kind of error measures are you going to use for that? And so research has used a lot of, because remember, it's all simple stuff. So they did a lot where someone had to use a mouse and they had to follow a cursor. And so what they did is they would use, that's a continuous skill versus like grabbing a cup or flicking a light switch or pressing a key, whatever, right? That's a continuous skill. And they wanted to look at maybe variables of stress don't affect reaction time for a continuous skill. They do, but they didn't know these kind of things. So one measurement that they used in terms of accuracy or error in continuous skills was called root mean squared error. And so they did this in research. And then what they would do is, so this is a pursuit task using a mouse. And so they would look at the error over time. So this is the cursor. And then this is where they were with the mouse. Sorry, the cursor. This would be like the target, and then the cursor is you. And you can see how much they were like in one overshooting or undershooting the target. Because this is over time, right? It's a continuous skill. So when evaluating error, you just look at the integration or the amount of error over time. So they're just summing all of the space in between the lines. That's called root mean squared error. So it is a error measurement for a continuous skill or continuous task. Everyone good with that? So I highlighted the most, like the two that were used the most in research because of the fact that they were the most important initially. It gives you a good background as to why or how they're used in research, but also because if anyone has the textbook, so probably Drew, that they talk about a lot of research, like different studies. You guys cool? Boom. Okay. So now let's talk about performance production measures. So Violetta, what is the performance production measures sort of evaluating? What's the difference between production measures and outcome measures? Anyone? Oh, there you go. Go Violetta. There's one final outcome. One is the steps taken to get there. Yeah. So like the movements, like individual movements, right? So let's look at outcome or production measures, sorry. So typically, the production measures are going to divide it up into 3 different categories. Kinematics, which is evaluating the movements of the actual body. Kinetics are the forces or the moments that are generated in the body itself, or in the sort of the environment. So think about like hitting a baseball, the force generating, like that's generated in the swing. So the movements may not be much different between someone that hits it very, very far, but maybe they're stronger. So you see that the force is a lot stronger in, one person versus another. And then neural measures are those measures that are going to evaluate EMG and brain activity. So these are going to look at movements, and then neuromotor processes are going to be evaluated by neural measures. So let's first talk about kinematics. And you guys have probably done this in biomechanics. Has everyone done biomechanics? Where you're looking at kinematic analysis. So kinematic analysis, you're evaluating movements of the body. And so there's a lot of different sensors that were developed, plus like photography research and like all different types of things, of ways to evaluate someone's movements or technologies. This gives us the kinetics of someone or their body. So it first started off with photography, right? So here's an example of way back in the day, someone figured out how to do multiple shots. And so they could do, what they could do is they could look at, what the movement of the body would look like. So this is an example of someone going up the stairs. So like, oh, they get slows down movement, because up to this point it was just visual, right? This is 1900. This guy developed this technology to take multiple frames. And so, let's see. So his claim to fame was that he proved that there's a period of time where so he's evaluating horse running, that there's a period in time where the horse's feet aren't touching the ground right there. So this was big news in 1900. And then fun fact, this guy went to jail right after for killing his wife's lover. But he did develop this technology. Here we have something more recent, obviously. This is a goniometer. A goniometer means something that measures joint angles. This is a manual one. We do this in rehab. I think I have one right here. That's in the other room. But it gives you a quantifiable measurement of joint angle, right? So you can look at like, it's sort of like you have someone's, joint contracture. They can only flex their elbow a certain amount, do treatment, measure it. Oh, it's better. I'm the best. Electrogoniometers are that would do it automatically. So this is an electric goniometer right here. It's measuring the angle between the two. So he's doing this in research. This is an accelerometer. You put them on your body and it'll measure accelerations. So this is, again, kinematic analysis. Here we have mechanical systems. So this was before photoelectric kind of stuff, but what this would allow people to do was measure all the different multiple joint angles over time. Here is one that measures back angle while they're doing a task. So it's a way of like giving you degrees or movements, right? It's giving you a production measurement, movement measurements. So here's an example of this being used in research, where they looked at how someone's like lifting technique, and they would look at their lifting technique in a live boat. And because it was a boat, they couldn't bring a lot of technology, so they had to use this. And they would look at what's the difference in the way that people move with a moving boat versus stationary, because same job, one in a factory, one on a boat, people on the boat are getting hurt. So what was the factor? Here we have magnetic systems. So this isn't an accelerometer. It measures the change in 3 planes of movement. So it's another way to get sort of the change in angle. You're not going to really be tested on this stuff. I'm just giving you an example. Here is probably something more similar that you did in biomechanics, where you looked at motion cameras. So passive is when a light shines these sort of reflective markers, whereas active, so an OptiTrack we have in our labs at Ontario Tech. Here, I'll show you the difference. So see how these are just shine or illuminated by a infrared light plus a camera. So what happens is a program has to go and sort of like put these all together after processing. Whereas with an active system, see right here, only one of these lights will go on at once, and then it's recorded by the camera. So the camera doesn't get confused as to which marker is which, because only one's going at once. It's just really high speed. So the problem with active cameras is that technically you can't measure fast movement or as fast movements because it's only using one marker at a time. Whereas this one, so here's like video game analysis, so like motion capture. Am I confusing you guys? Or you guys okay? Just to give you examples of different technologies that were utilized to evaluate kinematics. Because once we evaluate someone's movement, we can get a better idea of the movements that were used in the motor skill, and then we can look at that change over time if there's any, or look at variables that would alter that. Using kinematic measures, we can develop displacement measurements, velocity measurements, and acceleration of the body or joints. By using kinematic analysis, we can develop sort of like coordination measurements. So angle to angle diagrams are something that's been used in research. So you take the angle of one joint, like the hip versus the knee, and then you divide it out to make a graph. And then so you can have a measurement that like sort of technically evaluate coordination. This is just something that was used in research. So it's called an angle-angle diagram. So this is something that's been, as an example, being used in research to measure coordination. But it's still a production measure because it's evaluating the movements, not the outcome. This tells you if someone's joint angle over time. It doesn't tell you if they achieve the goal of kicking the soccer ball into the net, for example. Kinetics are measuring forces. So it involves sort of external things like force plates, force transducers, strain gauges, things that evaluate the actual amount of force put on the body or on external objects. Have you guys used force plates in biomechanics? Hopefully this is all sort of a review. Boom. Okay. Now let's talk about neural measures. So neural measures are going to be those measurements that are going to be measuring neuromotor processes. So it's going to give us a measurement of like sort of like the electrical activity in either the brain or the body that's used to control our muscles and therefore be utilized in the movements that are used in the achieving of a particular motor, the goal of a motor skill. So neural measures are evaluated or divided up into two different things: muscle activity measures and then brain activity measures. Remember that we contract our muscles utilizing the motor unit. So we activate a certain number of motor units for a particular muscle to get it to contract by a certain amount. And that's how we contract our muscles. So a motor unit is one alpha motor neuron, all of the muscle fibers that it specifically innervates. So what we do is we use EMG to measure motor units, and that gives us a measurement of electrical activity in the muscle. So it's the most common. So what we did in my research is what we did in the slides previous. It's also utilized in fractionating reaction time, remember? But it allows us to give a measurement of how much a muscle is contracting because you can look at how much relative to max the muscle is contracting. So it gives you a measurement of muscle contraction. So that's going to help us in evaluating potentially the movements that someone's used in a motor skill. Whole muscle mechanography is another type of transducer that measures like sound. It is another way to look at electrical or activity of a muscle, whether or not it's being used. It's not used a lot, but this is gives us an idea of using a measurement to look at different muscle fiber composition. So not only is the muscle contracting, but is it slow twitch or is it fast twitch, for example? That may be necessary. Remember, like if you're doing plyometrics, you're trying to use more fast twitch and train fast twitch. So maybe that would be important to use whole muscle mechanography. Near infrared spectroscopy, sorry, is like the the blood, like as at the hospital or seen at the hospital where they have the infrared thing that goes on your finger. It measures blood oxygen. So they have one that is used to measure the level of oxygenation in the muscle or the brain, which would give you an idea that the muscle is being used. Actually, now, what we're going to be doing in my cerebral research is we're using HD EMG. So instead of using 2 bioelectrodes, we're using like 64. And so you can actually evaluate individual like motor units. So like, again, like, and more research continues and continues and continues, we'll be able to evaluate more and more things. And in all different fields, not just sort of biomechanics or motor control or neuroscience. Any questions about this, guys? On an exam, you would just need to know briefly what was on these slides. Here's an example of a tracing foot EMG. So here's an example. Let's say this was on like a thumb muscle. Here, the muscle is being utilized because you're reading electrical activity. Here's an example of how it was utilized in research in sort of motor control study, for example. And so what they did was this guy's like, so the task that they were doing for the research was they were just, oh, one second. And then he says, how do you isolate muscles with that equipment? Oh, it's where you put the pads. So if you want to look at the bicep, you put the pads over the bicep. If you want to, like so for here, they had someone at the go signal. All they had to do was raise their hand like this. So they had to flex their shoulder like that. That's all they had to do. Okay. And they measured electrical activity from the anterior deltoid, the ipsilateral hamstring, and the contralateral hamstring. And so what they wanted to look at is when performing that task. So we had the go sign, and they wanted to see what muscles turned on and in which order. So the task was this, and it looked at what muscles were, I don't know what order muscles were activated. It was actually the ipsilateral hamstring, then the deltoid, then the contralateral hamstring. Interesting, right? So it gave you an idea that, right, like, so remember we talked about in neuroscience, the premotor cortex, you got to activate the stabilizing muscles first. Here's an example of stabilization. So let's talk about motor control, right? I mean, this seems like a very, very like simple finding, but that means that you don't say, okay, I'm going to contract my arm and then the other muscles sort of react and then you stabilize. That stabilizing occurs in the brain. That's all processed. Do you guys get that? Anthony, you good with that? Boom. This was my study. This is way back when I was doing a master's. This is, what year was this? 2010. That's way pre-pandemic. So what we were looking at was looking at the activation of the shoulder muscles with different loading conditions. We were funded by the automotive companies, and they were wanting to look at why in certain jobs people were getting injured, like lifting stuff, versus other jobs where they weren't. And when there was like kind of seemingly dissimilar tasks. And the problem was that we found that when you're having to grip something, or when it's cold and you have gloves on, you have to grip that much harder, you contract your rotator cuff a little bit more, or that much more, which cumulatively would lead to the buildup of an injury faster. So if you're super interested, you can Google that. Here is examples of brain activity measures. So instead of reading electrical activity in the muscles, this time we're going to be looking at electrical activity in the brain. The most common that it has been utilized is EEG. It measures electrical activity in the brain, where you put different electrodes all over the scalp, and then it reads the electrical activity and where it is. So it gives you an idea of what parts of the brain are being active and when. Transcranial magnetic stimulation is used a lot. We're going to use it a little bit in my research, but it's used by Dr. Murphy a lot. And what this does is it is a coil that it shoots part of the brain and turns it off. So you get someone to do something, shoot the brain, turn a part off, and then do the same thing. And then it gives you an idea of like, so how it changed, because you turned off that part of the brain, then you can infer what that part of the brain does. So again, these are measurements or sort of ways to evaluate brain activity. Here we have a TMS coil, so it's shooting part of the brain while the guy's doing a hand dynamometer task. Other techniques that are available are positron emission topography, or PET. It's looking at blood flow. So what you do is you take a radioactive dye, and it's not like harmful, but then you look at those dyes because you can read where the dye is, like so blood flow. So if the dye is in the blood, you can look at how much blood is and where. Then you can look at get someone to do something, and if you have more reading in one part of the brain, that means more blood's going there, meaning you're utilizing it more. So which part of the brains are being utilized for what? fMRI is kind of the same thing as you looking at blood flow through oxygenation levels. The most common one now, the most important one, or the most newest one now, is called magnetoencephalography. Now, the problem with EEG, which measures electrical activity, is small electrodes. So it's only measuring the top layer because it's got to go through the scalp. Now, how much of our brain is using just the cortex? It doesn't really tell us that much, right? Like how much is going on inside? We need to know all of that. And so a way to do that that was developed is MEG. And it measures the magnetic fields and therefore gives you electrical activity in the brain, but throughout it gives you a 3D picture. So here we have an example of an MEG machine. Now the problem with this is that think about what kind of motor skills can you do by having this huge thing strapped to your head, right? But here's an example of a study where what they would do is they did like a tapping task. So they had someone play a metronome and all the person had to do was click a button. So you had to click the button on beat and then versus off beat. So let's say like click, 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 or beat, 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 and they had to tap on beat. Or they instructed someone to tap away from beat. So click, 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 and so the opposite. And then they measured the difference in electrical activity, and they measured what parts are different and giving you an idea of like sort of what is actually happening inside of the brain. I think I have a video for you guys. Yeah, so this is an example of a MEG machine. And it won't let me do comment, preview, bam. 444 make a wish. A wish for better MEG machine.
Brain activity is basically just electricity.
Can you guys hear that?
So measures the magnetic fields that are generated by brain activity inside your head.
Sweet.
It's one of the few ways we have to get access into the internal workings of your mind. Lock the sensors, yeah. Okay, we're going to play you a sentence and we're going to ask you to covertly repeat it. That is, imagine saying it covertly.
The MEG has a built-in helmet of 160 magnetic field detectors that scan and record the subject's brainwaves every time she imagines a given word.
The book is next to the glass.
The MEGs are looking for a signal given off by neurons that's incredibly tiny, a field that's 1,000 times smaller than a refrigerator magnet.
Every millisecond, that is every thousandth of a second, we're recording from the entire head, from all 160 channels. It's an enormous amount of information that we then have to sift through to make sense of.
Their goal is to isolate clear efference copies for every word imagined by the subject.
You don't just know some word and its sequence of sounds. All the information associated with that concept suddenly comes up. Imagine yourself saying the word cat. You had a cat called Fluffy when you were a kid that threw up a lot on your bed, or you hate cats, you love cats. So it's not a needle in a haystack. It's like a needle in 10,000 haystacks.
Oh, wow.
With each word that Popel deciphers,
Okay, keep going.
we grow closer to a future where advanced mind scanners could lay bare our innermost thoughts.
It will redefine doctor-patient relationships. It will help redefine lawyer-client relationships. It will certainly have an impact in criminal justice investigations.
Imagine that you're going to the airport. TSA could figure out whether you are a terrorist or not. And it shouldn't be the case that TSA, by default, gets access to our thoughts. It would only be that people who want to participate in this sort of accelerated screening can opt into it.
Neuralink. No, tell us about it, Abin. Actually, I think I kind of heard about that. Do you have a link? You want to share your screen and tell us about it? Maybe next day? Guys? Someone answer Abin. Okay, so Abin is going to do a little bit of a presentation next day on Neuralink. Or you can just let us post a link and then I will oh, is it? Nice. Okay, someone click on it. I feel if I click on it, it's gonna screw up the presentation. But cool. So here, I'll read this after and then we'll talk about it a little bit next day. Cool? Is that okay, guys? How do we feel about Elon Musk? I think it's pretty cool. Pretty cool. Yeah, I like Elon. Yeah. Be a good friend to have. Okay. Yeah, he is I saw the meme. Okay, so we're just gonna finish off now. The last thing is talking about motor ability. So this was just a topic that was touched on when they started evaluating like performers in research. Is there a way, like, so think about like an all-around athlete. Is there a way to determine how good someone's going to be at a new skill based on how they are in other skills? Like, because that's going to be a factor that like, okay, well, maybe there's just some people that are better at motor skills, or maybe there's a sort of people that are good at certain motor skills and not other motor skills. And you look at another type of person and they're good at one thing versus another. They wanted to understand sort of like, what are the ingrained specifics of our, or people in general's ability to do motor skills. So think about ability as a adjective. Is it means like it's a general trait or capacity of a person to achieve something, or their ability to, hold on, I just said use. It would be their potential for achieving something in a particular field based on their ability in that. So an ability is a relatively enduring characteristic, and it is the determinant of a person's achievement potential for performance of a specific skill, right? So that guy is really able, or he has a good ability in this. It means they have a nice potential or good potential in achieving that. Does that make sense? I kind of butchered that, but the term ability. So when looking at the term motor ability, we're looking at someone's potential at achieving a goal in a motor skill. So if someone has a high motor ability, they're going to be good at learning motor skills versus someone that has a low motor ability. They're going to take a lot longer to learn motor skills, right? So researchers wanted to just quickly understand, is there specific motor abilities? Is there one motor ability? And that just tells you like there's only one type of motor ability and you're either good at it or not good at it. Or there are 8 different motor abilities: timing, hand-eye coordination, speed, balance. And then you have like people that are good in some and not good at others. Who knows, right? Let's research it and figure it out. So they developed 2 different theories: the general motor hypothesis. So general motor ability hypothesis, that means that there's just one motor ability, and all motor abilities are someone's like timing, rhythm, balance. It's all highly correlated. There's a general motor ability that someone possesses. And then there was the group that said there was a specificity of motor ability hypothesis, meaning that people have different motor abilities, there's multiple different motor abilities, and an individual will have varying degrees of ability in each of those. So depending on the person, they may be good at balance but bad at rhythm, or they may be good at timing but bad at hand-eye coordination. Okay? So research looked at that. They measured people's abilities in different types of things and looked at whether or not you could predict or correlate the two. So the general motor hypothesis said that all motor abilities are highly rated together, and then a person can be described as having an overall amount of general motor ability. Whereas this one, the specificity of motor abilities hypothesis, said that all motor abilities are independent, and then a person varies in the amount of each ability. And so lots of interesting research that was developed, and it proved the specificity hypothesis. And it showed that it's sort of independent of each other, that someone could be good in one motor ability and not good in another. So it sort of disproved this whole idea of a general motor ability. Here were some of the studies that they did. They looked at like static versus dynamic balance. They looked at external versus, oh my God, I just screwed up. They looked at external versus internal timing. And so you can go through some of this stuff, but all of what it did was looked at how there is times where different motor abilities aren't relatable or they're not correlated. So it kind of disproves this whole general ability hypothesis. Here's an example of timing. So if someone has good internal timing, then they should be able to in this study, the person had to tap to a metronome, draw a vertical line to the metronome, draw a horizontal line to the metronome, and then draw a circle to the metronome. And so you would think that if someone had an ability, they would all be the same, and they look at differences in the same individual. So it just kind of it showed that things aren't correlated very well, sorry. And so then the question is this whole idea, this is Bo Jackson. I don't know if you guys know who Bo Jackson is, but there used to be athletes that would play multiple sports, right? Professionally. But I mean, think about people that you know, that everyone knows someone, or maybe you, that they just seem to be good at all sports. So if the general motor ability hypothesis doesn't exist, how do you explain that there are some people that are just good in all sports? And it's because they decided that it's probably because a lot of the sports that we have are all involving the same sort of things: running, hand-eye coordination, jumping, speed, right? So it's people that are good in all those kind of things are going to be generally good at sports. Does that make sense, everyone? Cool. Like we had talked about Gentile's taxonomy last day. You're not going to be tested on this and sort of using it. But there is a taxonomy of motor abilities that was devised by Fleischmann that wanted to look at sort of figuring out what are the smallest number of motor abilities that could exist. So he divided things up into perceptual motor abilities versus physical proficiency. And what he would want to do is he would want to use that like a taxonomy in rehab to look at what are the motor abilities of people, and then of a patient, and then you can look at which ones you need to fix. Now, this research led into the whole research of standardized testing. So think about a fireman, right? So there's people that are going to become a fireman or a police officer. There's standardized tests where they have to look at whether or not they're able to fill certain physical proficiencies, right? It's like an example of using Fleischmann's motor abilities taxonomy. Other ways to do it, if you wanted to coach, it would be what they call dividing up the tasks that you want to teach the people into the different abilities that are required. So then when you could look at the more skill that you want to teach someone, look at the different things that are involved in that particular skill. And then they looked at, so these are the different movements or the different types of variables that are involved in it, whatever you want to teach. And then using some of the classifications of motor abilities from this previous guy, you could look at, okay, well, this task is going to involve these abilities, and then train someone for that. Now, most people don't use a taxonomy. This was just an example. He was trying to develop some sort of guideline. Most people do it intuitively based on the sport that they're trying to teach or the rehab skill that they're trying to teach. So that's the end of the lecture. Is there any questions about motor abilities? I just wanted to touch on it very briefly. Any questions, guys? Awesome. So before I go, I wanted to just discuss, I did that posting about the virtual labs. So did you guys all read the virtual labs thing? So some of you may not know, but we're in a lockdown. There's a thing called coronavirus, and we all have to wear masks. We're not allowed to go outside. So unfortunately, we're not able to have in-person labs. So oh, Matthew's an anti-masker. Okay. Oh, okay. See, I flushed it out. Hopefully the feds aren't reading this. So did that make sense to everyone, that posting? So now labs are going to be a link where you watch the video about what the lab would be. You answer embedded questions. There'll be like 2 or 3 questions just to show that you watched the video. And then you do the associated lab report and then submit that in through Turnitin. And then that will be 4% for each lab. Oh, yo, Matthew is canceled. You're gonna lit up on social media. But seriously, any questions about that? Like, I tried to like write it out as easy to understand as I could in the announcement. But does everyone make sense? Okay, do we have to log in or anything for attendance during our lab time? No. So what you would do is, if you have any questions for the TA specifically, you could email them. That's why I did it, like have their email, and then they will set up a Google Meets time with you, and then you meet with them. This is our first go at it, like trying to figure it out. It may be that everyone has the same questions and the TAs are overwhelmed with answering the same questions over and over again. So maybe in the next coming weeks, we'll figure out that it's probably better to have a scheduled thing. But for right now, what we're going to do is post the video, and then you just do the lab on your own time. And then they're technically due when the next lab would be. Yeah, so for Nicholas, the labs are asynchronous. I thought that was the fairest way to do it. Yeah, people did say that the labs were really fun for this class, so it's sort of unfortunate for everyone. So they're not done yet. So the kin labs are actually doing them as we speak. Eben says, are the labs available to complete now? So yeah, well, you guys don't have any sample data or the videos. So the lab report is there. I have posted the lab report. It'll be super sus if you guys hand in the lab report from without the stuff being distributed. Like if you got like results from somewhere else, it's gonna look bad. Yeah. Oh my God, no. Megu just developed her own lab, just handed in her own lab report. Smart. So any questions, guys? We good? Oh wait, Jay asked, is there a certain time that the pre-lab has to be completed by? Well, no, you just have to complete it before you can like hand in the lab. So just do it. Because you're gonna have to view it to get the results to do the lab. Everyone good? Just thumb up, you guys. That's weird. Okay. Okay. Awesome. Hang in there. Have a good week. Bye. Turn off. How do I turn off?